Look around you. Everything you see, everything you are, was forged in the heart of a star. The iron in your blood, the calcium in your bones, the gold in your ring. These are the ashes of ancient stars. But gold and platinum need something even more spectacular: the collision of two neutron stars. In that fleeting, violent moment, the universe forges its rarest treasures. Today, scientists try to recreate these cosmic forges in the lab, unlocking the secrets of the gold in your ring. To understand the R process, we can't just look at the final elements, like judging a cake by its appearance. We need the recipe, the unstable, short-lived nuclei created in extreme conditions. Scientists use particle accelerators to smash atoms together, producing exotic nuclei that vanish in a blink. It's a race against time to isolate and study these rare ingredients before they disappear. Cutting-edge experiments are pushing the boundaries, revealing how the universe forges its heaviest elements. Scientists set out to study the rare decay of indium-134, an exotic atom packed with neutrons. Using a powerful particle accelerator, they created the purest beam of indium-134 ever gathered. The atoms decayed in a state-of-the-art detector, transforming into tin isotopes. For the first time, they directly observed a nucleus spitting out two neutrons at once. But instead of chaos, the data revealed a surprising order, almost as if the nucleus had a memory. What does it mean for a nucleus to have a memory? Imagine the indium-134 atom as a complex, tightly wound ball of string. When it decays, a piece of it, a proton, transforms into a neutron, creating the tin-133 nucleus. This process leaves the new nucleus in a very specific, highly ordered configuration. The standard picture assumed that the nucleus would immediately forget this initial configuration, shaking itself up into a chaotic high-energy state before randomly ejecting a neutron. Think of shuffling a deck of cards thoroughly. You don't expect to see any patterns from the previous game. The experiment showed the exact opposite. The tin-133 nucleus didn't forget. It seemed to remember the simple, orderly state it had just been created in from the indium decay. Because of this memory, it didn't just eject a neutron randomly. Instead, it decayed in a way that preferentially formed specific, simple states in the final tin-132 nucleus. It was as if the deck of cards, after a quick shuffle, still retained the memory of its previous order. This non-statistical behavior was a complete shock and challenges decades of established nuclear theory. This discovery is profoundly important. Our computer simulations of the R process, the ones that tell us how much gold a neutron-star collision should create, are all built on the assumption that these decays are statistical and chaotic. This new evidence suggests that our models might be wrong in a fundamental way. If nuclei can remember their past, it changes the probabilities of which pathways they will follow as they decay towards stability. This, in turn, changes the final amounts of heavy elements like gold, platinum, and uranium that are produced in the cosmos. We may need to rewrite a significant chapter of our cosmic cookbook. Ultimately, this is a story about the power of curiosity. It began with a young researcher looking closely at the data and noticing something that didn't fit. It was driven by a team that built a better experiment to chase a deeper truth. It reminds us that the universe is always more intricate and surprising than we imagine. Each question we answer leads to deeper, more wonderful questions. By seeking to understand the tiniest, most fleeting particles, we unlock the grand story of the cosmos and our own connection to the stars.